Okay, thanks. So I want to talk about a few things related to the theory, what we can say about the progenitors, the emission mechanism, and so on. And I'll take a relatively big picture perspective. So first, I want to talk about a few things that we can infer more or less directly from observations. And the first one has to do with the central engine. So by central engine, I mean the region from which energy is tapped to power the FRB. And the basic observation there is that the duration of the FRB is short. And so the maximum region from which you can tap energy is basically the speed of light times that duration. And since this region is unlikely to be moving relativistically, there are no extra complications here. And you find a few hundred kilometers, which suggests something like a neutron star or black hole. You can go a bit further, and you can ask not just about the central engine, but also about the emission region itself. So there you could have a situation like you see here, where there is an outflow that is moving relativistically away from the central engine. And in that situation, you get a modification to just c times the relevant timescale. The typical timescale that we care about here is actually the variability time, which might be a bit shorter than the full duration of the FRB itself, but you get this extra correction, which goes as 2 times gamma squared. I can talk a bit more about it later on if I have time. And so the emission region might be quite a bit larger while still explaining these durations and the variabilities that we see. There's a third scale that is important here, and that is the lateral size of the source. So this is the region here in yellow on the slide, and this is the region from which photons can reach the observer and still be detectable in a significant amount, which is basically determined by the 1/gamma angle above the line of sight from which beaming is still large. So this decreases overall this previous radius by a factor of gamma, and this will also become important a bit later on. So the next thing that I want to mention is the magnetic field. For in fact, most of the models that we are dealing with for FRBs, the magnetic field at the point that either emits the FRB wave or at least launches the outflow that ultimately will emit the FRB wave needs to be sufficiently large compared to what? Compared to the magnetic field that is associated with the FRB wave itself. And as you can see, when you put the numbers, this already becomes quite constraining and tells us that it has to be a pretty magnetic environment. Now we can do a bit better, and we will get back to this equation in a moment, by looking at the luminosity. So the luminosity is extremely bright. In extreme cases, it can be as bright as 10 to the 45 ergs per second. And we can compare that with maybe the most natural source of energy that we can think of in neutron stars, which is the rotational energy. So in a typical pulsar, we have this picture that we see over here, where we have a magnetized neutron star with a magnetic axis that is misaligned with the rotation axis. And this thing, as it's rotating, it's emitting along the polar cap, which is aligned with the magnetic axis. And the emission is dipole radiation. The region over which it's beamed is to do with this region of open field lines of the polar cap. And so we can estimate the isotropic equivalent luminosity from this kind of situation. And what you get, you'll see it over there. You can put it in terms of 2 parameters. Typically, people put it in terms of the initial spin period and the magnetic field. But an equivalent way to put it is in terms of the initial spin period and the spin down time. And this is a bit more useful in terms of things that we have strong constraints on observationally. And the point here is that the number is just orders of magnitude too low compared to the power that we see in FRBs. So it's simply not powerful enough to instantaneously power FRBs. So we need to think of something else. And this something else might be magnetic energy. That's the other source of significant energy that we have in a neutron star. But let's see how much magnetic energy we actually need. So one good example is the case of 121102, where there was a long monitoring of this source, and they measured with FAST how much energy came out in bursts from the source. This is still subject to beaming, and we also need to take into account that there's a certain small efficiency of the radio luminosity compared to the true energy that is likely to come out in these systems. But you can fold those into the calculation, and you can compare that with the magnetic energy reservoir and put a lower limit on the required magnetic field. And you see that the numbers that you get when you do this exercise are very large, about 7 times 10 to the 13 in this simple estimate. And you see that there's not much freedom here. Beaming on the one hand is unknown, but efficiency sort of cancels it in the other direction. So it's not clear how much you can gain from this factor. And the lifetime, we know that the source has been around for at least 13 years. It's not evolving so quickly that we would expect it to be very close to that age. So 30 years is relatively conservative age estimate. And already you get very strong Magnetar strength fields. So just from these simple observations, we kind of reach this picture of neutron stars, not rotationally powered, probably magnetic powered. And the last thing is we can go back to the magnetic field at the launch point that we mentioned earlier in the slide. And here, if we take just as a very simple example, a dipolar field structure for the magnetic field, and we compare that with the magnetic field that is required to power the luminosity that we see in the FRB itself, then this puts an upper limit on the radius of emission, and you see that again, this upper limit is small. So suggesting that whatever is happening very close to the surface of the neutron star. This can be either the emission radius or the launch point of some outflow. Okay, so indeed, this may not come as a surprise because you all know that FRBs are associated with magnetars, at least some of them, right? So we know that the galactic magnetar SGR 1935 produced this very nice FRB back in 2020. And there are other evidence that connect FRBs to magnetars. This comes in the form of host galaxies, offsets, arrival time statistics, polarization properties, and so on and so forth. But really what I want to emphasize here today is one more link to magnetars, which has to do with magnetar wind nebulae. So this will be the topic of the next talk given by Minu, and he will discuss this model in detail. But the idea here is that in the few cases where we have an association with a persistent radio source, this is very constraining in terms of the underlying physical picture. If we interpret this as a magnetar wind nebula, then it puts strong constraints on the preceding supernova that led to the formation of this magnetar. Actually, perhaps counterintuitively, the supernova cannot be too bright because that will push the ejecta too far outwards. So we actually need a relatively weak or weakish supernova to have happened. And the other point is that the source of energy can be, again, either rotation powered or magnetic powered. But if you take a rotation powered source, you find that with magnetar strength magnetic fields, the energy is deposited too quickly. And by the time we reach tens or hundreds of years after the formation of the neutron star, most of this energy has been lost to adiabatic expansion. So this actually does not work out. Magnetic powered might work, but again, it requires some quite extreme parameters and might teach us something about the identity of these sources with persistent emission. The other point that has to do with the magnetar wind nebulae has to do with the polarization. And we know that FRBs are often have a high degree of linear polarization, but not always. In some cases, we see circular polarization as well. One way to do this, which is not coming from the emission mechanism, but from a propagation effect, is Faraday conversion. So Faraday conversion is something we expect to have in magnetized plasma. And typically, it's a weak effect of the order of omega B over omega, unless one of two things happen. Either the magnetic field is changing orientation very, very rapidly, or we have electron-positron plasma, in which case the typical angle of this rotation in the Stokes, in the Poincare sphere of the polarization vector is misaligned from the V component of the Stokes parameters. And then you can indeed get a large circular polarization by this effect. So this puts some very interesting limits on some FRBs. In some sense, it's pushing in the opposite direction to what is needed to power PRSs. because you need a very clean electron-positron outflow, which may not be consistent with what is needed if you want a magnetic-powered outflow with lots of ions and so on. So this is work in progress by Om Gupta, and hopefully we will have something out on this relatively soon, but there is a lot to learn about the progenitors. Okay, so talking a little bit about the models themselves, there are broadly two categories of models. One is the magnetospheric type of models where the emission is happening very close to the neutron star. This can be curvature radiation. It can be inverse Compton scattering of some tremors on the neutron star surface, forced reconnection, and so on. And the other category is far-away models. By far away, we typically mean emission outside the light cylinder. Perhaps the most famous example of this class of models is the blast wave model, where some blast wave is launched and at some large radius produces synchrotron maser radiation, which is supposed to give us the fast radio bursts. And the nice thing is that these models are quite significantly separated in terms of scales. So the faraway model really is quite a lot further out than the nearby models, and that gives us an opportunity to examine which one of them is consistent with the observations by doing various tests on the observations that we have. So I want to describe briefly a few of those things. And the first has to do with variability, both spectral and temporal variability. So this picture is showing you some outflow that is expanding, and you see emission of different photons from different points in this outflow. And there is a nice coincidence that people who work, for example, on gamma ray bursts know very well, which is that you have three different time scales here, which are relevant to dictate the light curve, and they all happen to be of the same order. So you have the time scale of the radius doubling, you have the time scale of difference in arrival of photons from the front and back of the shell, and you have the time scale of the photon, of the difference of arrival between photon coming along the line of sight and the maximally misaligned photon that can still reach with high probability, which is 1 over gamma above the line of sight. All of these are of the order of R over 2C gamma squared, and this gives very specific prediction for the shape of the light curves and the type of variability that you can get in these situations. And to make a long story short, unless you invoke some things that lead to significant inefficiencies, what you get is that the spectral width coming from these models is, cannot be too narrow. Delta nu over nu is of order unity, cannot be much less than unity. And the variability time cannot be much shorter than the FRB itself. T FRB over T variability is also order unity. You can also have this limit that is shown over there at the top, where if you know the flux at some frequency and some time, there is a minimum level of flux that is unavoidable at some lower frequency and slightly later time. So you can have a flux that is beyond that, but below is impossible. This is just coming from this high latitude emission, even within the 1 over gamma cone above the line of sight. And we have some observations that already are pushing against these limits. So you see here an example of an FRB with a very rapid variability time compared to its duration. And you see an example here with of an FRB with a very narrow spectrum. And these things are very useful to constrain the models. We talked a bit earlier during this conference about cases where we have co-detections with different telescopes of the same FRB. These will be extremely useful, and the more data we have that we can apply to this thing, the better, because we want to really see if this is a generic property of all FRBs, or if there is some class of models that maybe are consistent with a different type of emission mechanism. These things are important to clarify. One last thing that I want to mention in this context of separating the models has to do with scintillation. So actually, we got a very nice introduction by Wesley in the previous talk, who emphasized the importance of this effect. And one specific application of this that we discussed a couple of years ago is that if you have scintillation in the host galaxy, this can be very useful to tell something about the lateral size of the source that I mentioned back in the first slide. If the lateral size of the source, as projected onto the scintillating screen, is large compared to the diffraction length, this would lead to weak modulations If it's small compared to the diffraction length, it would lead to large modulations as a function of frequency. And this idea was then taken by the Chime team, and in this very nice work led by Kenzie Nemo, it was shown that there were two different scintillation bandwidths in this particular FRB. One of them clearly can be identified to the host galaxy, and this puts a very nice upper limit on the lateral size of the source. And as you can see from the figure on the right here, this is already marginally inconsistent with the most faraway models. And just to put it in sort of more illustrative terms, if you think about this in terms of angular resolution, the fact that we can resolve a region of 3 × 10⁴ kilometers from such a distant galaxy, it's the equivalent of an angular resolution of about 10⁻17. This is about 6 orders of magnitude, almost finer than what you get with the best image that we have in astronomy, which is the M87 black hole, but it's using a trick. And the trick here is that just like the camels in this picture over there, what we are observing is not the camels themselves, but the shadow of the camels on the dunes. So we are using scintillation as a way to get this projection effect and see in detail something that we shouldn't have been able to see. So this is quite remarkable, and I think if we can do this for more FRBs, again, this is extremely useful, both in terms of constraining FRB physics, but also just the fact that we can learn about the ISM of galaxies, distant galaxies, is very non-trivial. Okay, so moving on, I want to next talk a little bit about polarization. So the same FRB actually that was used for this scintillation analysis has another very interesting property, and that is this very nice polarization angle swing that is seen for the FRB that you see on the top right over there. And the question is, what does that mean in terms of the modeling? The level of polarization degree for this FRB was very large throughout, of the order of 95% or so. And this is something that is very unlikely to happen in faraway models because it requires the magnetic field to evolve with radius in a very particular way. But even if you do that, because of this high latitude emission, the photon that is coming from some large radius along the line of sight is arriving together with the photon from a larger latitude and a smaller radius, and that will cause depolarization because they will have different polarization angles if your magnetic field has evolved with radius. So that is unlikely. More likely that the magnetic field at the source is highly dynamic, or that we are somehow scanning a region of the source that goes over an angle greater than 1/gamma, and we're probing different magnetic fields in this way. This is something that is not a new idea. People in the pulsar community are very used to this, and this is the standard interpretation of pulsar polarization angle swings, which are a common observed phenomena. And the idea is basically that you have this polar cap that is sweeping across the line of sight, and as it does so, you're seeing different projections of the magnetic field, and therefore you get this nice polarization angle swing. So it could be an indication that we have a similar type of thing happening in the FRBs, and this will suggest magnetospheric emission. It also puts a very strong lower limit on the Lorentz factor of the emitting particles, such that we see a small enough region around each one of those magnetic fields with the well-described orientation, and we don't get too much depolarization. So again, there's a lot that can be learned from these types of observations. It's useful to compare this FRB, which was a non-repeater, with the observations of repeaters. We heard a very nice talk earlier this week about some more repeaters with this kind of data. This is a slightly older plot of 121102, where you see that both within a given burst and between different bursts, the polarization angle appears to be flat, while the polarization degree is very large. So this seems to be quite different than what we saw for this non-repeater. And it brings us to the more general question of the diversity of the FRB phenomenology and all the apparent similarities and differences between repeaters and non-repeaters. So I want to spend a little bit of time on that. So another point of diversity is the energies. The energies of FRBs span a huge range, about 9 orders of magnitude for those that we have confirmed redshifts for. This is just a sample of some of the FRBs, repeaters and non-repeaters that can be put on this diagram. The same goes for rates. If you consider the rates of fast radio bursts, they vary by a huge amount. The galactic magnetar produces a significant FRB maybe once every several years, especially if you think of all galactic magnetars as potential sources of FRBs, the rates will be even lower. Whereas active repeaters can produce bright bursts once every few minutes. A recent-ish study by Chime, 2 years old by now, shows that actually, if you look at all the repeating and non-repeating sources, and you try to constrain the repetition time for each one of them, the distribution between repeaters and non-repeaters is consistent with being continuous, meaning there's no obvious need for two populations in that sense. It's just a sort of tip of the iceberg effect that we are seeing with the repeaters. Here on the right, you see an example of the different rate that is assumed, that is obtained for 1945, the galactic magnetar, compared with the other FRBs. This relates to another point, which is how common these sources are in the universe. And the density of these sources is also varying by a huge amount. If you look at something like very active repeaters, say 121102, and you can try to categorize it as some class, let's say, very active repeaters associated with PRS, or something like that, those are extremely rare in the universe. Roughly 1 per gigaparsec cube is an estimate for the number density of these sources. Whereas if you look at something like galactic magnetars, even if only one of the galactic magnetars in our galaxy can produce FRBs, just the density of Milky Way-like galaxies is so large that you reach numbers that are 7 or 8 orders of magnitude greater. So this is a huge range, and again, there is a clue there that is important. In terms of distances, as brought by dispersion measures, the differences are not huge between repeaters and non-repeaters, but there is some difference. Repeaters are slightly closer than non-repeaters by a few tens of %. In terms of spectral and temporal properties, we've already heard during this conference that there are some differences between repeaters and non-repeaters. Non-repeaters tend to be shorter in duration and wider in their spectrum, and the repeaters vice versa. And all of this kind of prompts us to ask the question, what does it mean about the origin of FRB repeaters compared to non-repeaters? So in an earlier work this year, we suggested one possible geometric interpretation for this. And our idea is that non-repeaters might be instances of misaligned cases where the magnetic and spin axis of a magnetar are misaligned with each other, and the magnetic axis happens to sweep across the line of sight. And active repeaters are cases where you have this very rare, but we saw from the previous slides that very rare is okay. It's in fact something that we need here, alignment between the magnetic axis, spin axis, and the observer axis. And this explanation seems to have a nice way of explaining the data that is observed, both for non-repeaters and repeaters. So for polarization angle swing that we saw in non-repeaters, this becomes now a natural thing as you're sweeping across the line of sight. Also, the time scale works out very naturally with the typical periods that we think are relevant for magnetars. It also explains those twin bursts that we heard about earlier this week in the talk by Bera, where it can be just coming into and out of the cone of the polar cap. And when it comes to repeaters, it does a whole list of things for us. It explains why we don't see short timescale periodicity. This has been a puzzle for a long time in fast radio bursts. Why, if FRBs are associated with magnetars, don't we see a second or sub-second periodicity scale, which we expect those sources to have? If they're always along the line of sight, then you won't see that in the arrival time data. They're always on as far as you're concerned. In terms of the energetics, it boosts the effective beaming factor, because now all of the bursts, even if they are beamed, are preferentially coming towards the observer. So that explains, it helps with relaxing the energy requirements. It explains why there's little to no polarization angle swing between bursts and within bursts of active repeaters. It also provides a natural explanation for the spectral-temporal dichotomy. I won't go into this explanation. I can talk about it later if you like. And it explains the tiny ratio between repeaters, estimated number source densities, and those of non-repeaters, or if you want, the ratio of observed repeaters to non-repeaters. There are some predictions which I will just leave here, but not discuss due to time. And I will just move to the last thing that I want to say, which is that independently of this geometric picture, we later in the year, just out last month, we did another work, which is taking a very agnostic point of view and just asking, can all repeaters and non-repeaters be part of a single population? And the key observation that we realized here is the following, and that is that if you look at the number density of sources as a function of the rate at a given energy, and it's important to do it at a given energy of different sources, then you see this very nice anti-correlation between the two. And this is just coming directly from data. There's no modeling here. And so it roughly goes as one over the other. And this tells us that the more common sources are less active and vice versa. Once you account for that intrinsically, everything else comes for free. So once you account for that, you can, without free parameters, automatically reproduce the repeater to non-repeater ratio. You can reproduce this tiny fraction between number of non-repeaters that is seen by something like chime to the number of sources that we think are out there, up to the maximal distance detectable by chime. And by sources, I just mean something like magnetars that we have in our own galaxy. It explains this very large range of activities and source densities and energies and all those things that we've discussed. And it explains also why repeaters are slightly closer than non-repeaters. It's simply a selection effect where the fact that you've seen them twice makes it more likely to have had them at smaller distances to begin with. So I can go into more details perhaps during the questions, but for time I will not elaborate more at the moment. I'll just show you my conclusions here and take any questions. Thank you.
Thank you, Paz, for really impressive talk. And yeah, maybe we can start from Wesley.
Yeah, thank you. I was confused about the isotopic influence because it matters whether you've got 10 to the 45 or 10 to the 41 ergs per second. And you said that beaming does not help, even though I would have thought beaming actually does gain you 10 to the 4 because that you just say, well, every spark goes off in some direction, so you only see some small fraction of them.
Yes.
And then, of course, the isotopic is a hard bound because you know every observer presumably will see the same flux. But you're saying it's not. You're saying
no,
again. I didn't.
It's there. So I will. Oops, I'm going in the opposite direction. I will explain exactly what I meant there. So let me just go back. So here, in terms of the energetics, the beaming comes in, and you see that the beaming that comes in is this effective beaming. Meaning exactly what you said, that if bursts are beamed, but also pointed at random directions, then what you gain from the fact that each burst is actually not as bright as the isotropic equivalent, it has less energy, is also the same factor that you lose by the fact that you're missing out many of the bursts that are beamed away from you, right? So those two factors cancel if there is no preferred direction for the beaming. The way to bypass it is with some kind of geometric reference.
I didn't quite follow. So you put luminosity up there, which is 10 to the 45 ergs per second.
Mm-hmm.
Energetics is 3 times 10 to the 45 in 56 hours, which is about 10 to the maybe 36 ergs per second.
Yeah, the 10 to the 45 ergs per second. 10 to the 45 ergs per second is the most extreme cases that we have. It's not the typical FRB luminosity. So if you look at the typical burst that is detected in this say series of bursts detected from 12, 11, or 2, they have much less. But
10 to 30, but 10 to 30 is still much larger than 10 to the 41 divided by 56 hours, right? 56 hours is 10,000 seconds, so that's good.
Yeah. So
you're saying
a huge ratio between the largest luminosity that we see for a given FRB
Yeah.
And,
No, but
and the other thing is that 56 hours, during this time, you cannot take this energy and divide it by 56 hours. That gives you the average luminosity, but most of the time, there are no bursts.
Yep.
The luminosity during a burst is a lot higher.
I understand, but if it's beamed, you don't care. So if it's beamed, are you saying, I don't know, maybe we are agreeing, but I would have said for the average energy conservation, and all I do is I take 10 to the 41 divided by 56 hours. Is that what you're saying, or that's not what you're saying?
It's essentially the same, yes. So if you take this 10 to the 41, which was released in 56 hours, that gives you a sort of average luminosity, and then you can multiply by a lifetime to say what is the overall output.
And that is what you're doing?
Yes.
Okay, good, thank you. Then we agree.
And that does depend on the beaming in the sense that it matters if different bursts are emitted in different directions, or if different bursts are all emitted in some preferred direction.
Sure, but I think the minimum energy is if they're just random, isn't it?
No, it's the opposite. If they are random,
they're all in the same directions, then you can have negligible energy.
Or you can have a lot, and you will be selecting on the cases where you see them, and therefore it will be preferential.
Yeah.
Then next question from Yogesh.
Yeah, I have a couple of questions. So one on the model, you explained that repeaters and non-repeaters may be just coming from same sources with differing activities. How would you explain the pulse width differences?
Okay, yeah, thanks. So this is a good question because it's one of the things I didn't have time to cover during the talk itself, but I do have a slide. So let me get to it. Somewhere here. Okay, so this is a work that we did with Brian Metzger and collaborators a few years ago. The idea here is that we try to do some very simple toy modeling of FRB pulses. And we imagine that there are different properties. If it's the central frequency, the spectral width, the flux, all of these things might have some time evolution that come from the model. But we just want to see how they affect the observations. And what we found was that the single most important parameter is the rate at which the central frequency sweeps down as a function of time. And so basically what you can get with this type of model is the following. If your beta is relatively large, then what you get is that this pulse sweeps down through the entire observed band relatively quickly. And that ends up dictating the timescale of the burst. And so you get that the timescale is short because it swept through before it ended being active, but the spectral width is large. Whereas in the opposite case, when this beta is very small, essentially there is no sweep. And so the spectral width is the intrinsic one, which might be narrow, and the duration is long because you see it for the full time. So in the geometric picture that I presented, if you now have a repeater, which is an aligned source, you're always seeing the projection of the same magnetic field. And therefore, if the properties of emission depend on the magnetic field, they do not evolve much. This beta will not be large, and you will get something that is spectrally narrow and temporally long, and vice versa for the repeaters.
Okay, thank you. And the second question I have is regarding, you mentioned linear to circular polarization conversion. So with that understanding, would we expect some sort of anti-correlation between PRS and the sources which show circular polarization?
We might. There are other factors that go into this that have to do with the magnetic field that we will talk about and the age and so on. But this might introduce some kind of negative correlation between those two properties, and it's worth investigating a bit more. But even a little bit of ions in the plasma really kill the Faraday conversion. And this was there in the plot. I can quickly get to it, relatively quickly get to it. So you see here the y-axis is number of protons relative to number of electrons. And you see that even when the number of protons is 10 to the minus 2 or 10 to the minus 1, it's already going to significantly open up this region where you have no circular polarization.
Thank you.
Okay, can I short question, please? Yeah.
If I have time, I have two questions. Maybe I could ask quickly. In the model, in the far field model, where if shocks are involved, wouldn't there be also some high energy emission predicted?
Yes, we do expect high energy emission. There's a sort of afterglow that follows the initial burst in those cases. Yes.
And it won't be detectable or?
So the higher the frequency, the shorter lived it is. So in X-ray, it's very short-lived. You really need seconds or less.
Okay.
Optical, it's a bit longer lived, et cetera, et cetera. So yeah, in radio, you can detect it even minutes or more after.
In the second question is in the misalignment that you're invoking to explain the non-repeaters. The rate, I mean, the number, the difference in number in the population, how does that constrain any sort of angle in the misalignment between the rotation axis and magnetic axis statistically?
So you're saying the difference between how many repeaters and non-repeaters we see?
Yes.
Yeah, so that is a more involved question. We can talk about it maybe offline, because probably there are more factors than just the alignment. And there's also magnetic field, intrinsic magnetic field that is important, and the size of the polar cap, et cetera. So it's not something we directly get from this result, but we can talk about it more later.
Sorry, I'm really sorry that we are running out of time. So if it is okay, then maybe we can discuss offline. So let's thanks our speaker. Pause again.